So let us see more about stacks and queues. We'll see implementation of general purpose stack. As you remember, stack is a data structure where the latest member which has been added can only be removed. So stack can be naturally and quite easily, you can implement it either with your linked list or an array. So long as we dynamically resize it, the way we suggest for implementing a list, you will see in a short while. So for an implementation based on this linked list, we could, if this is a linked list, we could insert and delete either at the head or tail. Say this is head or this is tail. So either you can insert in the beginning, or you can insert at the last, or likewise for the removal. Both are roughly easy to implement, though inserting and this deleting at the head, this might be even easier, because even a single linked list have to do the certain things like to push an item, create a new element, link it to the old head and make it the new head. Okay, and to return or to read the top, it returns the head data item. And what about this popping off of the stack? It removes the head from the list and sets it next element as a new head. So let me show you. If this is head, so if you are trying to add this element, so head which was actually pointing to this will start pointing to the new one, and this node, the address of this node will be pointing to this. This is insertion. And how this deletion is going to take place? If this was our previous head, and let us have two nodes, they are linked, and this is our head which was pointing. So how to delete it? The delete is quite easy. What you have to do is you have to just point head to the next one, and this will be removed. None of these operations which we have just seen do we ever need to access any element's previous element. We have seen just now. So we can perform, we could also perform similar operation on the tail of this linked list. Same observation, just consider the last one, this element. So, but in order to pop the last element, we need to know its predecessor also, which will be the new tail. Because if this is the, say you have various nodes here, and this one is the last. So if you want to remove it, you need to know this one, because this is actually going to be having a null at the last. So we need the predecessor, which will be the new tail. So we would need a doubly linked list. For that, to know the previous one also, the address of the previous one or the information of the previous one, we need to have a doubly linked list. Or to scan through the entire list to find a new tail, you have to go to the last. So this one will be our cost ineffective solution. So better is to have a doubly linked list. And implementation using arrays is not much more difficult. We have an array, say A is an array. The name of this array is A, and store the size of the stack in some variable, say some size. And to push an item, we just need to write it into a size. Means if this is the position of size, then you just have to place that particular element at this position. And if we now exceed the allocated array size, we expand the array by allocating a new larger array and copying the data over, which was like the previous discussion of list we took. And to read to the top, what we'll do, a size minus 1 means this is the size because we are starting from 0. So the latest one we will pick up. Both the implementation means linked list and array, the running time of the top and or say knowing the top and pop operation is evidently it's order of 1 only. Okay, so we only return a directly accessible element and update only a constant number of pointers or integer variables. So we don't need more than order of 1 time to actually do it. And what about push? for pushing, the linked list implementation is also taking this much time. For the array element, this is order of 1, no doubt. But when you want to increase, or you need to, or you are forced to increase the size of an array, that will be taking this order of n time. And if you double the array size every time the array is too small, that is, which we learned that you can increment it by 1 or some 10% or double it, then for every operation that takes this omega n, the next n operation will require no doubling and thus take just order of 1. So those n plus 1 operation which we discussed earlier, this operation does take this order of n, which means that on an average they take order of 1. And this was actually an example of amortized analysis which was discussed earlier. Okay, we have talked about stacks. Let us come to queues. Queue provide first in first out, just like a queue in which you stand. It's just similar to that to access the data. And when elements are added in this queue, they can be read or removed only in exactly the order in which they were added, or in the manner in which they were added. The functionality of queues, storing element of some time t, is like adding an element. T is a data type. You can enqueue. Adding an element is known as enqueue. Looking at the element, maybe peek or see. You can use many books use many function name. And what about the remove? For remove, the name is dequeue or dequeue. And as we discussed with stacks, you would likely want to add a function which is called isEmpty. It's very important. And as compared to stack, you can only access the most recently added element in stack, while in queue it only allows you to access the oldest element. So much like the stack, we can define formally what is and isn't queue. So what is a queue? We have seen already this, that it may be an empty queue or of the form queue.enqueue data, empty plus some data, where queue is a queue and data is an item. And the precise semantics of this operation on a queue, we may discuss this somewhere. So implementation of queue, how it is going to take place, just like a stack, a queue can be implemented using a linked list or an array. So you can employ either linked list or an array. So for implementation using this linked list, we have two choices. First, we can just similar to the previous discussion of stack, you can insert at the head or read or remove at the tail. Okay, if you have this linked list, what you can do, say you have linked list, this is the last one, this is the head, this is the tail. You can only add at the tail and you can only remove from the head. Or the second option is you can either add at the head or remove at the tail. So the data structure will remain, or it will follow the soul of queue, but for the implementation purpose you can do like this. But in the second type, that is inserting at the tail and removing at the head, this has somewhat advantage, because singly linked list suffices when we delete. We only need to set this head is equal to head next and deallocate the whole, just head to next, as I just suggested few minutes earlier. So in order to delete at the tail, we would need to know the tail's predecessor. This is what we need if we want to do it or delete it at the tail. So we would require a doubly linked list or a linear time search, and for this implementation using arrays, because linked list is okay, for both the purposes you can have a singly or doubly, but when we are trying to use arrays compared to stacks, we now need two integer indices. One which is saying the newest or the latest for the position of the latest or newest element in the array, and one which says the oldest for the position of oldest element. And when enqueuing a new element, we have to write, or we can write it into a newest, that means on the top, and increment this newest, this newest plus 1. And to find out, that is to just see or peek front or see the top, we can just return the oldest and to dequeue the oldest element, we can just increment oldest by 1. And when enqueuing a new element and exceeding the current array size, we need to expand the array. This is always there with array. So one downside of this implementation is that it may be quite wasteful of space. So if the queue is used for a long time, after a while both newest and oldest may be large, which means that most of the arrays or array gets unused. So we could have an array which is wrap around by doing calculation of the index newest modulo the array size. So you can apply this modulo, so it will just space, and this is a new technology, not technology, but because it is a new way of how to reduce the there is one complexity called space complexity. We are talking about time complexity, but space complexity is also very important. So this makes better use of space, which we now have to be very cautious not to override this older element with the newer elements. So we may talk about all these obstacles, but one has to be a bit more cautious when you are actually implementing, which is based on linked list, which is slightly more attractive. So running time analysis is pretty much identical for just like stack, all operations of order 1, because they just involve dates of small number of variables. And as earlier, the only exception is possible exception of the array. Array has always this expansion of array, which may take order of n. So this order of n is quite considerable. So which we can again be amortized if the array size again doubles or gets multiplied by with some number rather than having sometimes or something added to it wherever the array is too small. So now we can discuss why use our restrictive data structures. Earlier we have seen a stack only allows access to the most recently added element, while a queue only allows access to the oldest element in the data structure. They both have their peculiar property. So somebody could argue that why to use this restrictive, why to restrict ourselves to these kind of data structures? This is a general question. Couldn't we have a data structure that allows access to either of them? Yes, the answer is yes, we can. There is a data structure called DQ, which does exactly what we are talking about. It allows adding and accessing element at the both end. So DQ is very important. If you understand how to implement this stack and queue, implementing a DQ will be far easy for you. So why wouldn't we use this DQ everywhere instead of this stack and queues? Why don't we use rather C++ vector class for all the data structures? C++ vector is unique in its kind. So it combines the functionality of stack, queue, and list in the sense which we defined earlier. It's very powerful also. But there are some answers to this. First is the pedagogical answers. We want to study how these data structures work internally, and using a powerful tool without understanding it does not contribute to studying. So one thing is we need to study about these stacks and queues. That is why we are studying here. Second answer or second argument could be we have to implement the data structure ourselves, right? So if we implement them ourselves, there's something to be said for keeping our data structure simple. But that argument does not apply when we use data structure provided in a programming language. And a third is often suitable answer to all this question that why are we not using a single for all these stacks and queues? The answer is that in order to implement more functions, the implementation of other functions may be less effective. For example, in order to allow access to each element in a constant time, the vector is implemented internally as an array. So it's going to be array only. So this is going to slow down the implementation of some other functions, which could be implemented quite in a faster way if we didn't also need access by index. And the final is that is the answer lies in our goal of writing code that we and our collaborators can define easily in future. So if you are going to write a code in which you are specifically using some variables as stack, you are making it clear that your code needs are specific to stack, which will help others parse the logic of your code. You had used deque and this vector types. Other may these data structures, other may have use, may not. You actually access specific elements or need to access both the head and tail in your DQ. This makes it somewhat harder to understand the logic. If you are providing the students at a first go DQ, he'll not be able to understand properly. So in general, it is always good to see the logic of both of them. So we could try our, to make this clear with our variable name, say by just writing something like vector in stack. But if we do this, it might convey our intention. Another interpretation can also be taken, that we had actually or initially written stack in stack, and then later understood that we actually needed extra functionality. But because we didn't want to rename the variable everywhere, we just changed its type to vector int. So even though the variable is called stack, it's not actually used one. So the upshot is that you should ideally declare your variable to be of the type that you actually need, not giving yourself extra functionality you don't intend to use. So in specific, you may not find too many immediate uses for a DQ, since most of the time you are very, very good or very much held by stacks and queues. So thank you so much. Hope you got the idea of queues and why we are not presenting DQ to everyone. Thank you so much.